Greetings. So, we have some familiarity with what quantum gates are, and we recognize that the principle of superposition is of fundamental importance in this. What superposition means, what entangle means, what the EPR paradox was, and how Bell's inequality help us resolve it or address it and find out what entanglement really means according to the experiments which have been performed hitherto. And we are now ready to discuss quantum algorithms. And there are three very famous algorithms. The first is due to David Deutsch. This was even historically the first one. This was the very first algorithm in the early 1980s. It came around the same time that Feynman pointed out that to simulate nature you really need quantum computers. And it was around this time that David Deutsch was also looking for a problem where quantum simulation would be of significance, of primary significance. And then of course there was Peter Shor's algorithm on factorization, which is again very famous. This came around 1994 or thereabout, and just 1 or 2 years later there was this famous algorithm due to Love Kumar Grover, which was a search algorithm. Now, we will have a chance to look at only one of these. So, I will give you just the introduction to the Deutsch algorithm and tell you what the Shor's and the Grover's algorithm are about, but you are going to read about those two yourself. And Deutsch algorithm is something that we will be discussing in this class. So, we are now working with two qubits. They could be two spin-half systems, and we will first consider the 2-qubit gate, which is called as the control NOT gate, or C naught, C for control, or CX, because the poly X gate is the NOT gate. So, these are the different terms by which this gate is known. This is the control NOT gate, or C naught or CX. And in this you use the 2 qubits. You identify one as the control qubit and the second as the target qubit. And what the control NOT gate does is that it performs operations on the target gate if and only if the control qubit is in a pure 1 state. Okay, that is the condition. So, the condition for operation on the target gate, it does nothing to the control qubit. It is going to operate only on the target qubit, but if and only if a certain condition is satisfied by the control qubit, which is why it is called as a control qubit. And the control qubit, the condition is that it must be in the state 1, which is actually at the south pole of the block sphere. Okay? Under that condition, it will perform an operation on the target gate. So, we will introduce this. It is represented by this symbol in the upper left corner, and you will understand this symbol as we discuss this further. So, the control NOT gate operates on a 2-qubit system to give you a new 2 qubits state, which is the one on the right hand side of this equation with a prime, and it will be it would operate on the target only if the control qubit is 1, and this is how it operates. So, this will be a 4 by 4 unitary matrix transformation, right. So, it will preserve the norm and so on. So, those are automatic consequences of a unitary transformation. And notice that the target states remain unchanged when the control qubit is 0. Okay. So, here the control qubit is 0, here also the control qubit is 0, the target is 0 and 1, and these target states remain the same, which is 0 and 1, and that is represented by this first 2 by 2 block of this matrix, all right. And here these states have got the control qubit is 1 and this is 0 and this is 1. So, this 0 becomes 1 and this 1 becomes 0. So, this is the control NOT gate, okay, because you see that 0 and 1, the 0 of the target state goes to 1 of the target state and the 1 of the target state goes to 0 of the target states. So, it is a NOT gate on the target qubit provided the control qubit is in the state 1. Okay. So, let us see how this operation goes. So, you have got the control qubit on the left, that is the block sphere on the left side of this figure. The target qubit is the block sphere on the right hand side, and in this picture both the control and the target qubits are in the state 0. So, in this case the control qubit, the control NOT gate will do nothing, right. So, it will give you from the 0 0 a new state which is also the 0 0, which is the same as the previous one, because the condition that the target gate undergoes a NOT operation is not met. Okay, so, this both remain at the north pole. Now, you have the control qubit in the state 0, which is on the north pole, but the target is on the south pole. But it does not matter where the target qubit is, because the control qubit is what controls the condition that the target qubit would be affected at all. Okay. So, things are going to remain the same, all right. So, from 0 1 again you go to 0 1, right. The target qubit continues to remain at the south pole because the control qubit is in the state 0, it is at the north pole. Now, we have the control qubit in the state 1, which is at the south pole. Okay, that is the control qubit is the block sphere on the left side of this figure. And on the right, the target qubit is in the state 0, which is at the north pole. So, now it will undergo a NOT operation and it will jump to the south pole. Okay. So, this is the C NOT operation. And then there is one more when both are at the south pole, but the condition that the gate would operate on the target qubit is that the control qubit is at the south pole, which is in the state 1, that is satisfied, and therefore, the target qubit would undergo an inversion. So, it will go from south pole to the north pole, right. So, that is the control NOT gate. So, this is essentially a 2 qubit quantum gate. So, we dealt with several 1 qubit gates in our previous classes. We did the Hadamard gate, the NOT gate, the square root of the NOT gate, the poly X gate, the poly Y gate, the poly Z gate, and then some phase gates. So, we did a number of single qubit gates, and now we are working with the 2 qubit quantum gate. So, this is the matrix representation of the control NOT gate, and it is represented by this by the statement at the bottom that AB goes to A comma A XOR. What is that? Exclusive OR. You remember that from your digital electronic circuit? Okay. So, there is an OR algebra which is which you can perform, but then there is an exclusive OR, and that is the truth table that this will follow, as some of you may have already recognized, but you will see it very explicitly. Because if you see, the control NOT gate takes 0 0 to 0 0, 0 1 to 0 1, 1 0 to 1 1 and 1 1 to 1 0. This is what we saw in the previous 4 slides, right. So, this is essentially the truth table of an exclusive OR gate of digital electronics. If you identify, you have got 2 inputs x and y, right, and if you identify x with the control qubit and y with the target qubit, you will see that the target is undergoing a change, in fact an inversion over here only when the control is 1, whereas when the control is 0, the target remains the same as the y input, right. So, essentially you notice that the control NOT representation is pretty much the same as the exclusive OR so far as the truth table is concerned, and you can therefore borrow this terminology from the classical XOR gate and use it over here to represent the 2 qubit gate, which is why this XOR representation is used over here on the 2 qubit gate. Okay? So, that is the symbol which is used because of its correspondence. You see a 1-to-1 mapping between the control NOT and the exclusive OR operation of classical digital electronics. So, this is the exclusive OR, which is written as XOR or EOR or sometimes EXOR, or X with a funny plus, okay, in a circle and then Y, right. So, these are the different equivalent representations of the exclusive OR operation. And before we proceed, I will like to remind you of what the Bell states are. They are also called as EPR pair, all right. These are maximally entangled 2 qubit states, and in our previous class we discussed these. The reason they are maximally entangled is because they cannot be factored into products of single qubit states, all right. And there are 4 such states, and we also analyze the reason why they cannot be factored. So, there is simply no way you can factorize them as products of 2 single qubit states. So, these are the 4 Bell states, and we will consider one of these. Let us consider the phi plus, which is root 1/2, which takes care of the normalization, and then it is a superposition of 0 0 plus 1 1. So, the first qubit is in state 0, the second is in state 0, and it is superposed with another component in which the first qubit is in state 1 and the second also in state 1. So, that is your Bell state. Okay. And if you carry out a measurement on this state and if it returns the value 0, then the probability that you will get this answer is only half, because it is a superposition of 0 0 and 1 1, right. So, the chance that you can a measurement will return the value 0 is only 0.5. The chance that it will return a value 1 is also 0.5. So, the opposite, which is 0 and 1, have equal probability. It is very random. Okay. But then if you carry out a measurement and you get 0, then there is no chance that the second qubit would be in any other state other than 0. Okay? Even if you do not carry out that measurement, okay, that is because of the entanglement. And if you did carry out that measurement, that is the exact answer that you will get. It is fully deterministic. Okay? So, the first one is fully random and the second, due to entanglement, is fully deterministic. So, this is a peculiar property of the Bell states, and this is now the representation of the control NOT gate, and now you understand the symbols and what they are doing to the control NOT operation, right. So, let us begin with a state which is 1 1. This is not an entangled state. There are only 4 entangled states, 4 Bell states in 2 qubits. Okay. We have seen what they are. They are here, the phi plus and minus and the psi plus and minus, right. So, anything else is not entangled. So, we begin with a state x which is 1 1. These are the 4 entangled states. So, the one that we have started out with is not an entangled state, which means that you can perform operations on the 2 qubits independently. Okay, you can carry out operations, an operation on first qubit without affecting the second and vice versa. They are not entangled. So, suppose you carry out a Hadamard operation H1 on the first qubit, right. What does the Hadamard do? It will generate a superposition of the first qubit. So, you get a superposition of 1 and minus 1 on the first, the second remains 1 and the result is a superposition of 0 1 minus 1 1. Is this entangled? Is this a Bell state? It is not. Even this is not a Bell state. So, this is also not entangled, which means that you can carry out further operations on this state also independently of affecting the other qubit, right. So, this is also not entangled. Okay. So, the H1 operating on 1 1 is also not entangled, and independent measurements on the 2 qubits can be carried out, and the uncertainty principle and the quantum entanglement is not affected. Okay. So, now you carry out the control NOT operation on this state which you have got. You started out with 1 1, you subject it to the Hadamard 1 1 to the Hadamard 1 H1, right, and you get 0 1 minus 1 1, there is of course a 1 over root 2 factor, and now you are going to perform a control NOT operation on this. So, the first term is 0 1, that will remain unaffected because the control qubit is 0, but the second one, the control qubit is 1, and therefore, the target will undergo an inversion, it will go from 1 to 0. So, are you beginning to appreciate the algebra of the control NOT gate now? All right. So, this is what the control NOT gate does, and what you have now got is in fact a Bell state. Okay. This cannot be factored. This is an EPR pair. This cannot be factored. This is the superposition up down minus down up. Okay. This is the Bell state. So, this is what you get by this operation, and starting from an unentangled state. We started with 1 1 which was unentangled. We put it through a Hadamard 1 and then we put it through the control NOT, and now what you get is a Bell state. Okay. So, the control NOT gate, which is the MVP, the most valuable player in this. All right. Of course, you have used the header mud, but the most valuable player in this game is the control knot. So, the control knot is called as the entangler for this reason. It has done it, it has taken some help from header mud, right. So, this is a term which is associated with the control knot gate. It is sometimes called as the entangler. You get an entangled state through this operation, but suppose you subject it to control knot again. The result that you got, you subject it to control knot. So, what you are doing is you are operating by control knot square, right, and you end up getting the unentangled state that you had at the previous step. So, it is also called as a detangler. Okay. So, it entangles a detangled states and it detangles an entangled states. Okay. So, that is what a control knot gate does. Then there are other gates, swap gates, swaps 2 qubits. So, you notice that the 0 1 positions and the 1 0 positions are swapped, okay, and this 2 qubit gate is represented by the symbol which appears at the top of the slide, and it is not a trivial swapping like claiming that Google is spelled wrongly with 2 O's, which is incorrect because the first O should actually be in the second position and vice versa. All right. So, the swap gate has real impact. All right. Then you can define the square root of the swap gate, and I will let you verify this, because if you just take the square, you will find that it will give you the matrix for the swap gate. So, there are these are some of the major 2 qubit gates. Let me also introduce you to the 2 qubit control Z gate. We did the control NOT gate previously, or the control X, which is the poly X, right, which was a NOT operation. So, we did the control X. Now, we will do the control Z. So, remind yourself first of what the 1 qubit Z gate did. Okay. So, the 1 qubit Z gate, which was a poly Z gate, was represented by the poly Z matrix 1 0 0 minus 1, right. There was a minus sign which you should remember, and what it did was to rotate the block sphere through 180 degrees about the Z axis, and the minus sign came because the x axis and the y axis, they got rotated, right, and the phase is measured with respect to the zx plane or the half zx plane. So, that is the reason you had a minus sign. So, this is what the poly Z gate did to 1 qubit, okay, and with this reminder we can now discuss the control Z 2 qubit gate. So, the single qubit gate essentially was a phase shift gate, and the control Z gate has this operation. So, the phase of the target qubit is shifted if and only if the control qubit is in the state 1. Okay. So, the logic is somewhat similar to how it was with the control NOT, the control X. Okay. But now the effect is different. What it is going to do is to change the phase of the target gate subject to that condition. In the control NOT, it inverted the target gate subject to that condition. In this case, it is going to change the phase. So, you pick up a minus sign and see that basically you have got the number 1 along the diagonal, except that in the 4th row, 4th column, it has a minus sign. So, it changes only that sign, it does not do anything else. Okay. So, this is the control Z gate, and we now are ready with our background in the control NOT gate, which is going to be again a main player in the algorithm we are about to discuss, which is known as the Deutsch algorithm. And he was actually trying to figure out what kind of a problem. So don't think too much about, okay, what is the use of this, and I can get this result doing some other things, right? Like you could do a good amount of arithmetic without using computers in your mind and then argue that, okay, why do I need a computer at all, right? Especially if you were joking like Feynman, right? He could do so much of arithmetic faster than anybody who used calculators. So Deutsch was looking for something which a quantum gate would do, which a classical gate cannot. Okay. So he was looking for some problem of this kind, and the problem that he ran into was this, that okay, if you have a certain function box with a certain input and a certain output, and I will tell you what input and output you are looking for, what kind of output do you get? Does it always depend on the input, or is it independent of the input? Okay, that is the kind of problem he was, and there are only two inputs. It is just a binary thing. The simple, very simple operation is what he was looking for. So there is a binary input which can be either 0 or 1, and the output can also be either 0 or 1. But what is the condition that you will get an output 0 or an output 1, and does it depend on whether or not the input was either 0 or 1, or irrespective of the input do you get a particular output? Okay, so the whole statement of the problem seems to be very simple. Nonetheless, it is a great illustration of what quantum computing is about, which is why the Deutsch algorithm is so famous. And of course, it is used in a large number of quantum circuits, because these are, many quantum gates which you put together. So the statement can be posed like this: is the function box in which you put an input and from which you get an output, is a constant or balanced? And you will understand these terms as I present the next table. So you are just dealing with a binary input and a binary output. Okay. The binary function, it is a function of just 0 and 1, right, and you really have only 4 possibilities. Your input can be either 0 or 1, and the output can be either 0 or 1, but then there are 4 possibilities. Look at the first column. No matter what the input was, whether it was 0 or 1, the output is always 0. So this is called as a constant function, okay, because the output is independent of the input. Then you have the identity, and identity is sensitive to the input. If the input was 0, the output will be 0. If the input was 1, then the output will also be 1. So it is sensitive to the input. You can also have the opposite of this, which is the NOT operation, but then again it is sensitive to the input, because you will get a result which is opposite of the input. So the input matters. And like the first column, you can also have a constant 1 output, which is again independent of the input. So you can have either a constant output in these two cases, right, or in the other two cases you have an output which really depends on the input, and if it depends on the input, the function is called balanced. If it does not depend on the input, the function is called constant. So, the question that Deutsch is addressing is the function box, is it constant or balanced? So, do you understand the terms now? Constant or balanced. So, suppose you are given a box, it is a black box and you do not know if it is constant or balanced, and you are posed with this question, tell me what this function box is. Is this function constant or is it balanced? How will you test it? And how many operations will you need to determine that it is constant or balanced? You can put a 0, find out what you get, you put another 1, you find out what you get, and so on. You can do again multiple operations. So, what is the minimum number of steps that you need to determine if it is constant or balanced? Okay, suppose you get 0 output, then you cannot be sure, you will not know whether it is constant or 0, because it could be constant if the input was 0, right, but the output could be 0 even if it was a not type of operation, right. So, you need to carry out some additional operation, and in the classical logic gates, if you were to use classical logic gates, you would need a minimum of 2 operations, 2 steps, whereas using the Deutsch quantum algorithm, you can do it in 1 step. So, do not worry about whether this problem is of interest to you at this point or not. Recognize the fact that you are meeting a situation in which a quantum gate can do something in 1 step for which a classical gate would need 2 steps. And depending on how you use your quantum gates smartly, you will have tremendous benefit of using the quantum gates. Okay, this is just the beginning. So, using the Deutsch quantum algorithm, you can achieve this in just 1 step, and we will discuss how you can get it in 1 step. So, the strategy is the following: use a quantum logic control NOT gate. Okay, we know what a control NOT gate is, but rather not just the control NOT that we talked about, but the function control NOT. So, it should also include the features of this function box. We do not know what that function is, but we know that there is a certain function, whatever it is, that is the unknown, that is something that you want to determine, right. But you set up a quantum circuit using the FCX gate, which is the function CX, which is the function control NOT gate, and then use Hadamard gates before and after this. Okay, so we will see how they help you do this, address this task of determining the nature of the function in just 1 step. So, the FCX gate will be used only once. Okay, that was the task, that the function box must not be used more than once. A classical logic gates can give you the result in 2 steps. So, that is not of great advantage, but if you can solve this problem, what you do before and after is not the issue. But the black box, which is a function box, must not be used more than once. So, this is what we are going to work on. We have seen what a control NOT gate does. So, now you see that the control NOT gate, it inputs x, y and the output is x and then x or y, right. You had the exclusive OR operation in the control NOT. So, that is what is represented here by that plus in a circle symbol. It means that that particular logic of the XOR truth table is followed, okay, which is what we have already seen is consistent with the control NOT operation. So, instead of the control NOT, we are going to use the function control NOT. Okay. So, what will come out will be the XOR operation result of the fx XOR y. Got it? So, that is the result that will come out, because you are using a function control NOT. Now, what you do is begin with insert pure states 1, okay, but pass them through the Hadamard gates before it enters the function control NOT gate. So, and then ask yourself what will be the state before it enters the Hadamard. These are pure 1 states. Then the Hadamard is going to scramble those, right, and then it will be subjected to the function control NOT and the output will be x and function as XOR y. So, that is going to be your result. Okay. So, you have the 2 Hadamards on the input 1 1, okay. You begin with input 1, both the qubits in state 1, right. So, you have got the 2 Hadamards. So, H1 and H2 on 1 1. This is an unentangled state. So, the operators would operate on those independently without affecting the other qubit, right. So, H2 will operate on the qubit 1 of the second qubit and H1 will operate on the state 1 of the first qubit, and this will happen independently because these are not entangled. And from the pure 1, you scramble them up and get a superposition 0 minus 1 in both the operations. And now you have got a direct products of these 2 vectors, these 2 states, right. And you can carry out the multiplication and the result is 1 over 2, because 1 over root 2 appears twice from the Hadamard matrix, right. And then you have 0 0, 1 0, 0 1 and 1 1, but keep track of the sign. So, you will have a 0 0, minus 1 0, minus 0 1 and then plus 1 1. Okay, it is just direct product that we have carried out. Now, remind yourself of what the Bell states are, and this is obviously not a Bell state. How could it be? We actually got it by multiplying 2 single qubit states, which would be its factors, right. So, this is of course not a Bell state, it is not entangled state, and notice that in the Bell states you have only some of the combinations. You have the combination 0 0 and 1 1 in the first, in the state phi, and you have 0 1 and 1 0 in the state psi with plus or minus sign in between. But in an untangled state which is factored, you have got all the combinations. You have got 0 0, you have got 1 0, 0 1 and 1 1. So, there are 4 combinations which are possible. All 4 are present in this unentangled state, all right. So, this is of great value because now the Hadamard's, the two Hadamard's generate a state which has got all the four possibilities, and all of these four possibilities can be addressed at once in one step by the FCX gate. So, it does not have to look at it separately, which a classical gate would have required to do. That is the reason the classical gate needed two operations, but now this quantum gate is going to deal with all four possibilities at once, and you will see that this is what will lead you to the desired result of finding what the function is, whether it is a constant or balanced, in just one step. So, this is the advantage is coming from the fact that all the four combinations are admitted to these are addressed by the function control not gate, because we have used the Hadamard's like this, all right. So, this is what we now have, and the output of the function control not would be whatever came in, and the other qubit would be fx XOR y, right. So, you have to find this state psi c which is coming out of the function C naught gate, okay, and this is going to be the XOR of fx and y. So, obviously you have to use the truth tables for this, which you can do one step at a time if you like. And let me show you how it is done step by step. So, you will get fx XORed with y, this is x, 0 0 minus 1 0 minus 0 1 plus 1 1, and you will get fx XOR y you must get for all the four terms, because this is all taking place in quantum mechanics. So, this is linear operators, linear vector space, and if an operator is operating on a sum of 4, then the result is going to be the sum of the operator operating on each of the 4 and then summing up the result. So, that is the linear algebra that you are using. So, you have to determine these 4 terms which are written in the bottom row. So, what is f0 XOR with 0, because x is 0, y is also 0 for the first term. For the second term, x is 1, y is 0. For the third term, x is 0, y is 1, and for the fourth term, x and y are both 1. So, you will have to, for the first term, you will have to find f of x XOR y. So, f of x is f of 0, then this is y. So, this is f0 XOR y. That is what you will get for the first term. For the second term, you will have f of x, x is 1. So, this is f of 1 XOR with y. What is y? Y is 0. So, you will have f1 XOR y, okay, and similarly you have the other 2 terms. And you know what is what from the XOR truth table. So, this is the exclusive OR truth table of Boolean algebra, right. And let us have a look at the first term. X is 0 0. You are asking what is fx XOR y. So, what is f0 XOR 0, right, that is what you are asking. So, x is 0, first qubit is 0, you are now going to ask what the second qubit will be. So, that will be f of 0, because z is always equal to x when y is 0, and that you know from the XOR table. truth table, right? If y is 0, then z is always equal to x. So, here it is, y is 0, z is equal to x, here y is not 0, but here y is 0 again, and z is again equal to x, right. So, z is always equal to x when y is 0. So, you can find f0 XOR 0, which in this case will be f0. Now, we do not know what f0 is because we still do not know what the function is. It does not matter, it is f0. Okay, that is what we want to finally determine in one step. Okay. Second term, so f of control not 0 0 is 0 f0, is that clear? So, now the second term is x is 1 0, and you can use the same logic, which is fx XOR y. So, x is 1, and since y is 0, z again will be equal to x, but instead of the control not, we are using the control, the function control not. So, you have the function 1 over here, right. So, you got the second term, and now you can get the third term, which I need not discuss in details except point out that now y is equal to 1, all right. You have to determine function control not of 0 1. So, x is 0, but y is not 0 this time, y is equal to 1, and when y is 1, where is it? When y is 1, z is the opposite of x. Here in the second term again, this mouse is not very sensitive here. So, y is 0, but when y is 1, z is the opposite of 1, and that opposite is what I indicate by this bar on the top. Okay. So, that is the not f, if you like, right. So, this is the function control not of 0 1, which gives you 0 and f0 not, right. And then you have the fourth term, which is the last one, which is the function control not of 1 1, and now the first one is 1, x is 1 and y is also 1. So, z will be the opposite of what you have in the first column, which is not x but the function x, right. So, now you have got the output 1 f1 naught, and now you collect all the 4 terms. Okay. So, you have summed up all the 4 terms now, but we do not know what the function is. Okay. So, we are only halfway down the solution to the problem. Okay. We do not know what the function is. The only thing we know that is if the function is identity, then f1 is equal to 1, which is the opposite of 0, and it will be the opposite of f0 because f0 is constant, it is an identity. Okay. And if f is not, then you have this result, then f of 1 is equal to 0, which is the opposite of 1, which will the opposite of f0, right. So, if f is balanced, then f may be either identity or not, and we have analyzed these 2 cases. If f is constant, of course, then f0 is equal to f1. Okay. So, you have these results now, and even if you do not know the function f at this point, you have these results which depend on whether f is constant or balanced. So, now if f is constant, f0 is equal to f1. So, this f1 you can write as f0, So, you have only simplified this. Okay. This f1 you simplify as f0. This is the knot of f0, but f0 is equal to f1. So, you can just substitute these values and you can see that this state can be factorized between this f02 minus f02. So, this is one bracket, these two terms, and this is the other bracket. You have been able to factorize it, one of which is a vector which you are familiar with. You have met this qubit on the block sphere. The other term you do not know because you do not know what the function is. So, these are factored into the first qubit and the second qubit. You are able to do so because these are not entangled, right. And the first qubit is a point that you have met on the block sphere for the constant function. Likewise, so you have identified what these factors are. Now, in the second case, if the function is balanced, then you have f1 is equal to naught of f0 and f0 is equal to naught of f1, right, which we just saw in the previous slide. And then this result that you get out of the function control naught, you can simplify just as you did the previous thing and again factorize it as a product of two 1 qubit states, one of which is a point on the block sphere which you have met before, the other is an unknown state for the second qubit because you do not know what the function is. Okay. But the factorization is different. This is a different point on the block sphere, you have a plus sign over here, and in the previous case you had a minus sign. So, when you have a plus sign, you have what point would it be on the block sphere? You remember the block sphere? So, you have got this factorization, one with a minus sign, the other with a plus sign. What about the second factor? That is the second qubit. Is there any difference between this one and this one? So, for both constant and balanced possibilities, the first qubit is a different point on the block sphere, but the second qubit is the same. We do not know what it is because we do not know what the function is, but we do know that it is the same. So, the factorization is done differently in the case of the constant function and in case of the balanced function, and that was exactly our question. How do you determine whether the function box corresponded to a constant function or a balanced function? And now you have a factorization which depends on what kind of this function box was. In one case you have got one point on the block sphere, in the other case you get its antipode on the other side of the block sphere. Okay? So, these are the first one with the plus sign is the point on the block sphere in the xy plane where it intersects where the sphere intersects the x axis, and the second with the minus sign is just its antipode where the minus x axis intersects the block sphere in the xy plane. Okay? So, this was the block sphere and these are the points. So, you have the plus combination and the minus combination which are antipodes of each other. We have seen this figure earlier, right. So, these are antipodal points on the block sphere and this is what we now have got. So, for constant f you have this state which has got the minus x state and this has got the plus x state. The other factor for the second qubit is the same unknown. It is unknown, but whatever it is not an arbitrary unknown, it is the same unknown. Okay? And that is a great advantage, because now what we can do is we can run this output from the function control not through a Hadamard. Okay, because the Hadamard is a great gate which begins with a pure state 0 and gives you a superposition which is x, it starts with the pure state 1 and it gives you its antipode, right. And on the contrary, if you carry this out one more time, it will recover the previous states. Okay, so we have seen that. So if you just pass this output from the function C naught gate, the control not gate, the function control not gate, then whether you get 0 or 1 will tell you whether the function was constant or balanced. So you have done a lot of other things no matter what, but so far as the function box is concerned, you used it only once. Okay? So you have paid a price, but what have you gained? You have gained in getting a result using quantum gate by using that function box only once. And that kind of a condition is not hard to imagine. You can be asked to perform certain operation and told that okay, you can use whatever resources you want, but this particular resource I will let you use only once. So that is the kind of situation you have, and a classical gate will not let you do this. Classical digital electronics will not let you do this, whereas the Deutsch gate has achieved it by using the function f only once. So this is the Deutsch algorithm. Okay, and there is no classical analog for this. There is nothing in classical digital circuits that you can do to get this result. So in the previous class we also discussed how the quantum gates can be actually realized. So we considered the spin half system, and you can use the nuclear magnetic resonance. The proton has got a spin half and you can use proton magnetic resonance. There are other nuclei that you can use which have different spins, right, and these spins can also talk to each other. So there is the spin-spin interaction, but then I told you that one of the biggest problems in this business is the decoherence. So what happens is that even if you are able to get entanglement before you read out, the states could decohere, and they decohere through different mechanisms. There is what is called as the spin lattice relaxation or spin-spin relaxation, and then there are different relaxation times T1 and T2, and sometimes you have a multi-exponential decay. So there is a very complex mechanism. So decoherence remains a challenge, but using NMR, the 2-bit Deutsch problem was solved like 20 years ago, and such a NMR quantum computer was built 20 years ago, and many things have been achieved, not just the Deutsch problem, but also the other algorithms including Grover and so on. So I will stop here for this class. Any question on this?
So like in this case we know that Bell inequalities are the the states which are entangled, but if we have more than 2 bits or like
Bell states.
Bell states are entangled, but if you have more than 2 qubits, then how do we identify whether
So Bell states are basically maximally entangled states. Okay, that is the maximum entanglement that you can get. Factorization is impossible. When you have 3 qubit states, again you will have a situation where the 3 qubit state you may be able to write as a product of 1 qubit and a 2 qubit, in which case you have factorized, or a product of 3 1 qubit states. Okay? So, they are not entangled if you can factorize. A 3 qubit state which cannot be factorized like this will be the analog of the Bell pair or the UPR pair for a 3 qubit, and you really need a multi-qubit quantum computer. What Google has claimed has 53 qubits, 53 or 54. So, you really need multi-qubit entanglement, and then you have to be able to sustain it. It is a difficult experiment. It is a very difficult experiment. But it is very impressive that it has been done, and you can get an account on the IBM machine. So, thank you.